welcome to all of you in the second class from my side in this course. So, first of all I would like to mention what is the book which we are following. Let me write that book. Numerical methods for ordinary differential equations by authors are Griffith and Higham, and the book is published by Springer. So, this is the book which we will be following for this part of the course. Now, let me recall what we have done in the last lecture. In the last lecture, initially we have seen Taylor series methods. Then we saw Adams-Bashforth methods, and after that we looked at Adams-Moulton's method. So, Taylor series methods and Adams-Bashforth methods were the category of explicit methods. And both can be of different order, as we have seen that it is called TSP, and when P is 1 means it is first order accurate method. In that case it is called forward Euler method. Similarly, Adams-Bashforth method of order 1 is also called forward Euler methods. So, for the first category of method in both the cases are same, which is forward Euler method. While in case of a Adams-Moulton method, the first order method was called backward Euler method. And second was called trapezoidal method. Trapezoidal method in some literature is also called modified Euler method, and we have already seen that Adams-Moulton methods is a way to develop general implicit methods, and both of them are implicit. Backward Euler method is also implicit and trapezoidal method is also implicit, and that is what we have already seen in the last lecture. But if you look at the derivation of these methods, what we discussed in the last lecture, they were through the Taylor series by some manipulations of high order derivative term, etc. Now, in this lecture we can also see the alternate way of deriving these methods. What is that? Through numerical integration. That is what I am going to show now. So, suppose this is my problem. Okay. Let me integrate both the sides from xn to xn plus 1. Okay. So, now left hand side will become yn plus 1 minus yn, while in the right hand side we have to, of course, if we are integrating as such, then it is then it corresponds to analytical method, but our role is to derive the numerical method, for which we do not know how to integrate these terms. So, in that case, like that is the role of numerical quadrature formulas also, which you have seen in the previous part of this course. So, basically I wanted to integrate, suppose this is my function f x y from xn to xn plus 1. Okay. So, if for just for simplicity I am considering, let us say this is positive. So, if I choose the sample point at the left hand like this, then the approximation of this integration will be this xn plus 1 minus xn and f of n. So, which is basically h f n. So, it means it is a forward Euler method, and if I choose a sample point here at the right hand, which you let me show you, in that case yn plus 1 minus yn will become h into fn plus 1. So, it corresponds to backward Euler method. Why I am saying sample point? Because that is the way how you approximate numerical integral, by Riemann sum, by choosing the sample point. And if I choose the sample point at the average of both, in that case this will become this, or this, which is basically a trapezoidal method. Okay. So, we have seen, like if this is a function we are integrating from xn to xn plus 1, sometime we are approximating with the area under this curve with the help of this rectangle, and sometime we are approximating this with the area of this rectangle. Okay. So, we are overshooting the real area. In the previous case we are underestimating the real area. Sometime we are choosing with the help of trapezoidal, because this is the area of also a trapezoid, that is why it is called trapezoidal method. So, that is how you can also see that how these methods can be derived otherwise with the help of numerical quadrature method. So, though we have seen only few special cases like forward Euler, backward Euler, trapezoidal method, let me see one more case of implicit method, which is second order Adams-Moulton method, because we have already seen the difference equation of that method in the last lecture. So, again I am writing differential equation. Let me integrate it. This time I am integrating from xn plus 1 to xn plus 2. So, basically if we do this, and we approximate this function with the Newton's interpolating polynomial, which you remember from the previous part of this course when you must have derived the interpolating polynomials. So, this will be fn plus x minus xn delta of fn. So, left hand side will become this, and right hand side will be this, So, let me substitute x minus x n is h u. So, in that case the limit of u will become this, and this will become h du. So, this will become f n 3 by 2, because u square by 2 when I will substitute 2. So, 2 minus 1 by 2, which will become this. So, the scheme will be this yn plus 2 minus yn plus 1 is equal to h fn plus 3 by 2 fn plus 1 minus fn. So, this will be h into 3h by 2 fn plus 1 minus 3h by 2 fn. Sorry, this will be 1 minus 3 by 2 minus half. Okay, so this will be h by 2 3 fn plus 1 minus fn. So, this is the scheme we observed in second order Adam-Bashforth method, because just this starts from n plus 2. So, this is recursive. I can write yn plus 1 minus yn h by 2 3 fn minus 1. In the last lecture you must have seen in the following form. So, that does not matter, because n can be here, I am replacing n with n minus 1. So, we can get the following terms. Okay. So, I have also shown you how to derive these difference scheme with the help of numerical quadrature, which you have already seen in the previous part of this course. So, basically we have derived forward Euler, backward Euler, trapezoidal method, as well as we have also developed the difference scheme for a second order Adam-Bashforth formulae, which was not specified by the special name, but the difference scheme was the following, and it was explicit. Anyway, Adam-Bashforth methods are explicit. Moreover, the specific point about this scheme was that it is a two-step method, because there is a terms involving n minus 1, n and n plus 1. That is why it is called two-step method. Similarly, as I was saying that we can develop trapezoidal method also in the following way, but in that case I have to integrate. If you because last time what I have done, I have chosen the sample point at the average of 2. Okay, so that was through the, if you look at the definition of a Riemann sum as a approximation of a numerical integration, and but more formally if you do the following way, and then you interpolate this function with fn, this, you will get the same difference equation which we got in trapezoidal method. But now one specific thing about this and the previous case was that in previous case I was integrating from xn plus 1 to xn plus 2, and inside this interpolating polynomial, I was keeping the term which was involving only points at x is equal to xn. But in this case I am integrating from xn to xn plus 1, but still inside this I am keeping the same terms. So, why? Because we know accordingly we will get trapezoidal method is just a single step method. They involve term with n and n plus 1, while in case of a this two step method terms were involved n plus 1 and n plus 2 from here, n minus 1, n and n plus 1 here. So, that is why we have started integration from xn plus 1 to xn plus 2. So, it all depends how you want to manipulate and what are the terms you want to keep in your difference equation. Accordingly, you will get your difference equation. So, this is the alternative way of deriving the formulas for numerical solutions to OD. Similarly, you can also go for higher order, you can take 1/3 Simpson rule to approximate numerical integration, 3/8 Simpson's rule. So, there are lot of rules for that. Okay. So, accordingly you will get different type of a formulas or difference equations. Now just let me open the slides. Yes. So, now let me mention you linear multi-step methods. Linear multi-step methods, because so far we have seen single step method or two step method. In fact, we have seen only one variant of a two step method, which was the second order Adam-Bashforth method. The Euler method, trapezoidal method and the Adam-Bashforth methods are example of linear multi-step method. Single step, two step, all the both category comes under multi-step. So, linear multi-step methods are the generalization of Taylor series. Why it is a generalization of a Taylor series? Because you will see that when we were looking at the Taylor series methods, the term involving second order derivatives and higher order derivatives were kept as such, while in other cases which we have seen so far, the terms involving were having only y and the value of its derivative. So, that is what I am saying here also, and it relates the value of y and y dash x at several points. So, basically it relates the value of y and y dash x at several points. That is the difference in linear multi-step method and Taylor series methods. In Taylor series methods, terms also involves y double dash value of y double dash x, while in Taylor series methods we are relating only the value of y and y dash x at several different points. So, I will be explaining this in detail also. For the time being, we shall be concerned only with two step linear multi-step method. Of course, what I am explaining here can be generalized to more than two step, but right now our concern is just to derive two step linear multi-step method in general, like Adam-Bashforth method of order 2, which we have already seen. That involves the 3 level xn, xn plus 1, xn plus 2. For these we need to find the coefficients alpha 0, alpha 1, beta 0, beta 1 and beta 2, so that we are writing y x plus 2h, y x plus h, y x as well as the value of its derivative at x plus 2h, x plus h and x. And alpha 1, alpha naught, beta 2, beta 1 and beta 2 are beta naught are the coefficient which will be we will be choosing accord, and this is the truncation error. So, where p might be specified in some cases, means I wanted to, if I wanted to derive first order method, I have to specify p, and or sometime depending on the template we wanted to choose p, means what are the points we wanted to keep in the difference equation, accordingly we have to choose p. So, sometimes we might to try make p as large as possible. So, in this case we have taken alpha 2, which suppose to become here as a normalizing condition. We have chosen alpha 2 as a 1, the coefficient of y x plus 2h, that is what you can observe from here. And using y dash is equal to and dropping the term. So, once we started dropping this term, this is some equation, but once we start dropping the truncation error, it will be a difference equations. We arrive at general two step linear multi-step method, and LMM is the abbreviation for linear multi-step method, which we will be seeing now onwards. So, now this is your difference equation for two step linear multi-step method. Okay. So, if you observe this difference equation carefully, if I say beta 2 is 0, in that case this will be called explicit method. Okay. The method corresponds to this difference equation will be called explicit method if I choose beta 2 is equal to 0. But if I choose, because then there is a no term which will be involving yn plus 2 in the right hand side. So, that is the definition which we have already seen in the last lecture, corresponds to explicit and implicit methods. I do not need to repeat that definition again. While if I say beta 2 is 0, it is explicit, if beta 2 is not 0, it is a implicit linear multi-step methods. So, for example, in case of a Euler methods, when we got this difference equation earlier. So, basically it is an example of a explicit one step linear multi-step method, while the trapezoidal rule is a example of a implicit one step methods. You know, some people call it as a method, some people call it as a rule, some people call it as a formula. These are just synonyms of the same thing. Now, in order to streamline the process of determining the coefficient of this linear multi-step method, we introduce the notion of a linear difference operator. Because difference equation is here, it is clear to you, but how to choose this coefficient? Of course, we cannot randomly say that alpha 1 is 0, alpha not 0, beta 2 is something else and beta 1 is something else. We have to choose according to some process. So, what is that process? That I am going to explain you. The linear difference operator LH associated with the LMM is defined for an arbitrary continuously differentiable function yx by the following definition. So, here this is the definition of a linear difference operator which we are introducing right now, LH yx. So, what we are doing? We are taking the difference of the left hand side and right hand side term, if you observe this carefully. So, what should be our expectation from any difference equation? Our expectation of any difference equation should be that a linear difference operator should be of order h p plus 1, where p is greater than 0 for every smooth function p, because if p will be greater than 0, only then I can say that truncation error will tends to 0 as h tends to 0, because only in that case difference equation will approximate that differential equation. If truncation error is not tending to 0, it will not converge. That is what we have seen in the last lecture also. So, to define this truncation error concept in an alternative way, what we are writing? A linear difference operator LH is said to be consistent of order p if p is greater than 0 for every smooth function y. So, you can observe that consistency is necessary for the convergence. If you look at this more carefully, of course, consistency is necessary condition for the convergence, because basically this is a truncation error which should tends to 0, because when I proved the theorem in the last lecture corresponds to forward Euler method also, then also I was able to prove the convergence because truncation error was tending to 0 as h tending to 0. And of course, every time why we are calling as a linear difference operator, because this is a linear operator which you can check. because what is the definition of linear operator? LH alpha y1 plus beta y2 should be equal to alpha LH y1 plus beta alpha LH y2. So, this you can check, that is why we are calling it as a linear difference operator. So, an LMM whose difference operator is consistent of order p for some p is greater than 0 is said to be consistent. That is what I have already said. So, now though we already know that Euler method is consistent, because in fact we have gone one step ahead for that method, we have proved the convergence also of that method. But still by this way also we can start proving the same thing. The linear difference operator of Euler method will be this. So, again this yx plus x, and that is how we can define it. So, now I will be writing a Taylor series corresponds to this up to this term, and this is the truncation error, and then this I am retaining as such. So, this can be cancelled out with this, and this is here. So, basically LHYX is order of h square. So, this is just the same way to look at truncation error in alternate way, because this way helps you if some difference equation is also given to you, you can prove whether it is consistent or it is not consistent. That is one thing. Another thing is you can drive the method according to fixing the template. Template means what points you wanted to keep in the method at x, x plus h, x plus 2h. While in Taylor series that is not very easy task, because you have to approximate y double dash x, y triple dash x. Here order is also fixed, you can keep it. Okay. So, hence the method is consistent of order p. So, that is the advantage of looking this way. If difference equation is given to you, you can prove whether it is consistent or not consistent. Similarly, sometime you are very particular that only I am wanted to construct a two-step implicit method. So, I should fix the points at x, x plus h and x plus 2h only. So, in those cases it helps. Now, let me give you one example, because most of the time if you drive a difference equation through Taylor series, we end up with a consistent difference equation, because we leave the truncation error which is always order of h square. But if suppose some difference equation is given to you like this example. Now, our job is to prove whether it is consistent or not. So, for this let me define linear difference operator again, which will be yx plus h minus this. That is the definition of a linear difference operator which we have seen earlier. So, again if I write the Taylor series of these points, then this will be equal to yx plus h y dash x plus order of h square. So, this is the term I will be getting after rearranging term, because this will be get cancelled here. So, minus h y dash x will come here, h square and order of h cube. So, LHYX is order of h. So, hence the method is not consistent, because basically p is here, p is not greater than 0, p is greater than 0, because we have said in the definition that p should be greater than 0. So, this is the example of a inconsistent difference equation, which is very rare to see once we drive difference equation with the help of a Taylor series. So, because most of the time we end up with the consistent differences scheme. So, now in these two examples we have seen how we can prove that our method is consistent or not consistent. Now, in the next example, our aim is to find out what is the order of consistency of the following linear multi-step method or difference scheme. So, the scheme is given to us this. So, now if I wanted to determine the order, again I have to follow the same procedure. Let me define linear difference operator, which is this, using Taylor series expansion for this function and for this function as well as for these functions. And after rearranging some terms, you can see this is the term corresponds to yx, this is the term corresponds to y dash x, this is the term corresponding to y double dash x, y triple dash x. We will be keep adding the term till we get non-zero. So, because this is also, if you look at 2 by 3, this what is the calculation here, 2 by 3 plus 1 by 6 minus again 2 by 3, and here also. So, what if this is order of H5, if this term is non-zero, this will be order of H4, if this term is non-zero, this will be order of H cube, because this is 0. Let us do it, this is also 0, this is also 0. So, and here we have to see, so this is 4 by 3 plus 2 by 3 minus 2. So, this will again be 0, this we have to see. So, this will be 2 by 3 plus 1 by 6 minus 2 by 3. So, this is the non-zero term. So, this will be order of H4. So, the order of difference scheme will be 3 in that case. If LHYX is order of H4, the order of consistency will be 3, that is what we have already seen. So, this way you can also determine the order of any difference scheme which is given to you. If it is consistent difference scheme, you can determine the order. In fact, you can also prove whether it is consistent at all or not. That is what we have seen in the previous example. So, now generally, as we have already seen that consistency is necessary for the convergence. So, let us formalize those concepts of consistency in a more formal way with the help of characteristics polynomial. That is what we are going to do right now. For the general two-step linear multi-step method given by the equation 1, which we have seen earlier, the associated linear difference operator is this. Okay. So, now the method to be consistent, we must have LHYX is order of H square. That is what we have already seen, that it should be H p plus 1, where p should be greater than 0. So, for any difference scheme to be consistent, we have to put that this and this is 0. If that is not the case, you will not end up with the consistent difference scheme. So, 1 plus alpha 0 plus alpha 1 is equal to 0. 2 plus alpha 1 is equal to beta 2 plus beta 1 plus beta 0. So, we are formalizing these two necessary conditions for the consistency, or you can say for the convergence, in the form of a characteristics polynomial. The first and second characteristics polynomial of linear multi-step method is given by the following formula. This is called first characteristics polynomial and this is called second characteristics polynomial. Why we are calling it as a first characteristics polynomial and second characteristics polynomial? Because we wanted to redefine this condition in terms of characteristics polynomial, which is easy to remember and doing some analysis. So, the first condition corresponds to this becomes rho 1 is equal to 0. Okay. And second condition will become rho dash 1 is equal to sigma 1, because rho dash r will become 2r plus alpha 1, sigma 1 is basically beta 2 plus beta 1 plus beta 0. So, that is how we could get the second condition in the form of characteristics polynomial. So, basically what we have already said, we are writing in the form of a theorem. The two-step linear multi-step method which is given by this is consistent with the ODE which we are going to solve with the help of this linear multi-step method. Two step because the term is n plus 1, n plus 2, if and only if following conditions will be satisfied. That is what we have already derived here. Okay. So, the two-step linear multi-step method is said to be consistent with the ODE if and only if these two conditions are satisfied. So, basically you write either in the following form of a characteristic polynomial or you write in the following way. Both are equivalent way of saying the same thing. And now let me prove one theorem which says that a convergence linear multi-step method is consistent. Okay. So, that it means consistency is necessary condition for the convergence. Suppose that linear multi-step method is convergent and linear multi-step method corresponds to one which we have already seen earlier. This is this. Okay. The definition of convergence implies that yn plus 2 will, which is a solution of a difference equation at xn plus 2 will converge to this. Okay. So, here basically x star is xn. Similarly, using the definition of convergence we can say this also. Similarly, we can say this also as s tends to 0. This is the definition of a convergence we have seen earlier also. Since these points will also converge to xn as h tends to 0, taking the limit on both the sides. So, we are taking the limit of, means if this tends to xn, it means h tends to 0. So, once we put the limit h tends to 0, right hand side will be 0. We will end up with this, this and this. And then if we write in the form of a first characteristics polynomial, this will become this. In general, this cannot be 0 in general non-trivial solution. So, rho 1 should be 0, the first of the consistency condition. So, this is first consistency conditions which we always get with the help of convergent linear multi-step method or a difference equation which is convergent. For the second consistency conditions, we are rewriting the same difference equation, this in alternative way. We are dividing with h. So, this becomes this. Now, if we apply the limits, left hand side becomes this, okay, and right hand side is basically this beta 2. So, right hand side is basically beta 2 yn 2 dash plus beta then 1 yn dash plus 1. Okay. So, if left hand side will become this 2 plus alpha 1. So, all the things will, if you use the definition of a convergence, we can rearrange the terms in the following way and we end up with this, which is again the second consistency condition, because 2 plus alpha 1 is basically sigma dash 1 is equal to, sorry, rho dash 1 is equal to sigma, which is this second consistency conditions. Okay. So, we have proved that convergent linear multi-step method is consistent, because both the conditions should be satisfied, which is this or this. One is that first consistency condition, this is called second consistency condition. Okay. So, now we have seen the proof of the theorem. Now, let us take one example again. Determine the coefficient in one step linear multi-step methods. So, if you remember, so far most of the time whatever examples we have done to prove the consistency, their coefficients were given to us and we were proving whether it is consistent or not, or in one case in fact we have determined the order of the consistency. But this is the first example where we are trying to find out the coefficient of the difference equation. Okay. Determine the coefficient in the one step linear multi-step method and we are fixing the order, that resulting method has order 1. Okay. So, with the help of this example you will also learn how to determine the coefficient. Of course, this time I just for simplicity I have kept only one step method. So, we define the linear difference operator according to the definition which we have seen in the just now this way, and then we will collect the terms of yx, we will collect the terms of y dash x after expanding Taylor series for this and this. Okay. So, here I have skipped few steps which you can do very easily just by writing a Taylor series and recollecting the terms. So, for the consistency the coefficient of y and y dash should vanish, that is what we have already seen, because if it is consistent at least order of h square should be there, and in fact in this case we have said resulting method has order 1. So, like truncation error determines the order of the method, similarly consistency determines the order, because consistency is just the alternate way of looking at the truncation error. 1 plus alpha naught is equal to 0 and this is the second condition we are getting. Hence, the resulting linear multi-step method will be this, because from this equation you can get alpha naught is equal to minus 1. So, this is 0. So, alpha naught is minus 1 which you can keep it here, and then we get this beta 1 and beta naught is 1 minus beta 1 which I am keeping here. So, if you want that resulting method as order 1, it has given us some flexibility to choose beta 1. So, if I am choosing beta 1 is 0, so in that case we ended up with explicit method and which is same as the difference equation which we got in case of a forward Euler method. If beta 1 is 1, in that case of course this should be, this 1 should be here, this is just a little typo. So, yn plus 1 is equal to yn plus h, hence the scheme will be same as backward Euler which we got, and if I choose beta 1 is half, the scheme will be this which is trapezoidal method. And fortunately you will see if you expand this series and collect the terms of y dash x, one term will come from here. So, this will be h square by 2 y double dash x, and one term will come from here h beta 1 h into y double dash x. Okay. So, if you substitute beta 1 is equal to half, both the terms can be both the terms will be cancelled. So, that is why the resulting method will be of second order accurate, which we already know in case of a trapezoidal method. Okay. So, fortunately our aim was to resulting method as order 1, but when we choose beta 1 is equal to half, it corresponds to trapezoidal method, and the which we already know that it is a second order accurate method. So, the order consists LHYX in that case will be order of H cube. Okay. So, clear to everyone. So, this is the first example where we have learned how to find out a coefficient of a difference equation by keeping template fixed. What do you mean by template? Template means I wanted to retain only the points which use n and n plus 1. Similarly, and it is not my aim that whether I end up with the explicit method or implicit method, anything is fine. That is why we have kept the term Fn plus 1 as well as Fn. If our aim is to drive explicit method, then we would have kept this term with beta 1 0, or basically it means that we would have not kept this term at all. So, with this I am closing now. Thank you very much for your attention, and I hope everything is clear to you. Thank you.